Today we're going to graph quadratic inequalities. Let's refresh by graphing a linear inequality. This is in y equals mx plus b form. So my y-intercept is -3 and my slope is up 2 over 1. But remember, this is a less than inequality symbol, not a less than or equal to. So this line should be dashed, not solid. Our last step is to shade the region where all the solution points exist. To figure out which region that is, we can test a point such as 0, 0 and see if it makes the inequality true. If it makes it true, then that is the shaded region. If 0, 0 does not make the inequality true, then we shade the region where 0, 0 is not located. 0 is not less than -3, so 0, 0 is not a point in our solution set. So this portion is not shaded, but this one is. You could also visually notice that less than would be below this line. Any point that exists in this shaded region is a solution to this particular inequality. Now let's graph a quadratic inequality. This one is in standard form, ax squared plus bx plus c. So go ahead and find h, the x part of the vertex, by using -b over 2a. Plug that into the x's to get the corresponding y. Because a is -1, this is actually a less than, not a less than or equal. So go ahead and erase and use dashed lines. To find the shaded region, we're going to pick a point that is in one of the regions. 0, 0 seems like an easy option, and plug it in to see if that is a solution for our inequality. This is not true, so 0, 0 is not a solution, so we'll shade the region where 0, 0 is not located. Instead of shading the outer region, we shade the inner region, making all our solution points any point inside this shaded region. What about a point on the actual parabola? Would that be a solution, like the vertex? Let's test it. Oh wait, no, 0 is not less than 0, and that is why this is a dashed parabola, not a solid parabola, because the points on the actual parabola are not solutions, but the parabola is a border for all the solutions in the shaded region inside. A manila rope used for rappelling down a cliff can safely support a weight W in pounds, provided by W is less than or equal to 1480 d squared, where d is the diameter in inches of the rope. Graph the inequality and interpret the solution. Notice that we are in standard form, and a is equal to 1,480. 4 times 1480 is 5,920. You can see we have no horizontal shift or vertical shift, so our vertex is at 0, 0. That means I'm only going to graph 2 more points. I'll scale the x-axis to be by 0.5 and the y's to go by thousands. Because our vertex is at 0, 0, our rise values are actually the y values at each point. This is a solid parabola because our inequality symbol is less than or equal to, so now we just need to find the shaded region. We could test the point 0, 0, but the point 0, 0 is on the parabola, not in one of the regions to perhaps shade. So I need to choose a point that is in one of the empty regions, not on this actual parabola, to test. I chose the point 1, 1. And that is true. So we will shade in the region where 1, 1 is, which is below this parabola. So what does that mean in context of the problem? The x-axis is the diameter in inches, and your graph is not complete until you have labeled your axes. If I picked a random point in the solution set, d, w, the first number would represent given that diameter, the second number would be the weight the rope can safely carry. The set of solutions represents the max weight a rope can carry given its diameter. Pause this video and just graph the parabola portions of these inequalities. Make sure to make them dashed or solid based on the inequality symbol, then press play and I will explain how to find the shared shaded region. Now that we've successfully graphed the parabolas, let's shade the regions. For the first parabola, or the first quadratic inequality, let's test the point 0, 0 to see if it proves as a solution. Zero is less than 3, so 0, 0 is a solution for the upside down parabola. We will shade inside the upside down parabola. Let's test to see if 0, 0 is a solution for the second quadratic inequality. Yes, 0 is greater than or equal to -3, so 0, 0 is also a solution for the second inequality. So the inside of this parabola is the solution for this quadratic inequality. That means the overlap of the shaded regions is our solution for this system of quadratic inequalities. And our solutions would be any points in this overlap shaded region. For number 4, if this were a quadratic equation rather than inequality, the answers would be our x-intercepts, so we would want to maybe factor or use one of our methods to solve quadratic equations. I'll try factoring first. So you need your product of two numbers to be -4 and the sum of those two numbers to be -3. Now use the zero product property to find those x-intercepts, or the values at which the parabola intersects the x-axis. These x-intercepts are going to guide us for which interval or intervals contain our solutions. 4 and -1. My options could have solutions to the left of -1 and to the right of 4, or my answer could be solutions between the two. So we're going to check each interval. First of all, I know that -1 and 4 are not included because this inequality symbol does not have the or equal to below. Now we'll check our intervals. Less than -1, I'll choose a number like -2. Plug it in and see if it makes this inequality true. Six is not less than 0, so -2 is not one of our solutions. Now I'm going to test x equals 0. -4 is less than 0, so 0 is a solution, meaning the interval in which 0 lies will include all our x solutions. Let's do the algebra to verify that our next interval does not include solutions for this quadratic inequality. Because 16 is not less than 0, then we are correct. X equals 5 is not a solution to this quadratic inequality, and our solutions only lie between -1 and 4. So if I were to write the interval of solutions in interval notation, x's would have to be between -1 and +4, non-inclusive. If this were or equal to, we would have brackets instead of both parentheses.